It is really a pleasure to be back. I had to look up. We were here in 2013 was the last time. My wife Sally is here. We actually came here to graduate school for her. She had a fellowship in the wildlife ecology department. Worked in Yellowstone, and I was a chemical engineer as an undergraduate. In high school or college, I had never had a single biology class in my life. So I started taking classes while I worked for Dow Chemical. So some of the people who helped me, and they're kind of the reason that I'm here today, a guy named Jack Burke, who a few of you might know from Barber, Burke, and Pitts, plant ecology book. He taught at Cal State Fullerton. That was the first field class I'd ever had, field botany in California. Chuck was the first general ecology class I'd ever had. Martin Caldwell was my mentor here, who was extremely influential in my life for many reasons. And then my postdoc mentor at Stanford, Hal Mooney, was really the person who kind of got me to think about global change experiments and kind of the way the world is changing around us. And that's kind of the theme of what I want to talk about today. So thank you for being here, and thank you for the really nice intro, Chuck. So 2 seminars while I'm here. Today's a little more about greenhouse gases. There is some ecology in here, but we're going to do some other things today too. And then tomorrow, for those of you who can stand 2 seminars, is a little more of a traditional field ecology, plant and soil type seminar. So today I want to talk about greenhouse gas emissions, natural solutions, but also some maybe less than natural solutions. So I want to emphasize today, I want to talk mainly about this umbrella. So probably the thing that I enjoy the most that I do professionally from a research standpoint is to chair an organization called the Global Carbon Project. And I'm going to say right off the bat, we have hundreds of scientists that contribute to different budgets. So everything I talk about today sort of stands on the shoulders of every paper, in many cases, dozens of people's work. So I'm here sort of as an ambassador for GCP and also kind of helping to set our research agenda. My executive director, Pep Canadell, has been with GCP forever, and I'll try and credit some other people as I go along. So what do? We assemble budgets for greenhouse gases. Carbon dioxide was first, started before I was with GCP by people like the late Mike Raupak in Australia. Methane, I'll talk about today, those 2. Nitrous oxide, we'll come out with our first nitrous oxide budget in the next 6 months. And then we work on cumulative emissions and negative emissions. So cumulative emissions are how big is the atmospheric bucket for a given temperature threshold? How big is the bucket in terms of emission space to keep the Earth's temperature below 1.5 degrees and 2 degrees? And how much confidence do we have in those estimates, and how do we know what those relationships are? And so there's a great deal of work in that space. And then negative emissions are kind of running fossil fuel emissions in reverse. The notion that down the road we may need to actually pull greenhouse gases back out of the atmosphere if we're to stabilize the Earth's temperatures. So I'll talk about that for a few minutes today. But anyway, this is our group. And then I should say, philosophy-wise, we're a volunteer organization. Everything we do is publicly available, transparent. So any person out there can download all the data sets, analyze them for themselves and such. And then we also try and present our results at sort of different infographics and things at different levels. So we have certain products targeted to high school teachers, and other data sets more targeted towards researchers like many of you. So it's a great organization, and I'm lucky to be involved. So okay. So this is an example. I was at the climate summit that happened in New York a few weeks ago, and the WMO, the World Meteorological Organization, released this report that we led a part on emissions, and so it was called United in Science. Some of the take-home messages in that report got pretty good coverage. Average global temperatures have already risen 1.1 degrees. So when people talk about 1.5, 2 degrees, what's a safe increase? I should say that I'm not going to talk about climate change today, but we've had 43 years now in a row of above average temperatures. The chances of that randomly are more than 1 in a trillion. So there's no doubt that the Earth is warming, and warming very, very quickly, especially in polar latitudes. So we're well on our way to 1.5 degrees, and at current rates of emissions have something in the neighborhood of 10 or 20 years of emission space left before there's enough greenhouse gases in the atmosphere to bump us over that threshold. So it's close. And you think about the infrastructure of power plants being 40 years, cars being 10 years. So there are things, the embedded inertia of the energy system is immense. Last 5 years, warmest of any period on Earth, and we're starting already to see changes in increasing in food insecurity around the world, hunger again after decades of improvements and declines. We're seeing disasters. 2017, it's not just about our grandchildren. 2017, this country spent $100 billion more than we had ever spent before on climate disasters, and adjusted for inflation. So the previous record was about $200 billion. 2017, we spent over $300 billion on hurricanes, floods, droughts. So this is happening right now, and when we're paying for these changes already. We get, we do a lot of outreach work. We spend almost as much time on our communications as we do on our science. And this was you can't read it real well, but one of my favorite news magazines is The Economist, and The Economist had a whole issue on the climate issue, and they took a bunch of our data from this release and produced different graphics with it and things like that. So I'm almost as interested in communication and outreach as I am in producing the data and the science itself. Okay, so just a few slides on emissions. So sort of where are we? This is carbon dioxide emissions, billions of tons of carbon dioxide here, 1960 to 2018 on the right. This is work led by Corinne Le Carré in East Anglia in the UK. Last year, 2018, we were almost 37 billion tons of carbon dioxide for emissions. You see a general upward trend. Generally, when we have a decrease, it's when the global economy is in trouble. And we had, like here, the 2007-8 was a global economy crash, real estate, finance crash. In here, we had, for the first period of time, we had a hint of emissions that were flat while the global economy grew. And that's a really, even though we're not at peak emissions yet, that's the decoupling that we want to start to get to. But we're back to going up, and 2019 is going to be up again. So we have yet to even stabilize emissions, let alone turn the corner on those. And so why, just one slide on the energy infrastructure, why is it that we can have this incredible development of things like renewables and yet not be turning the corner? If we were in class, we would, I'd ask you for reasons for that. This is global energy consumption by fuel type. And then this goes back to 2000, I believe, here. The things in brackets are the growth rates for the last 5 years. So first of all, the best news, and I am a climate optimist, here's the renewable. So this is basically wind and solar. Right? So we're just getting to the point now where globally wind and solar is comparable to nuclear and hydro. Right, so this is an amazing transition. That's a doubling, it's 14% a year growth over the last 5 years globally. That's a doubling time of about 4 or 5 years. So that's the good news. The bad news is that these are going up too, with the exception of coal that we'll talk about. And these increases, even though they're smaller percentage-wise, are as big, or in some cases bigger than these increases. So basically everything is going up, and that's being driven by increased energy consumption overall. So most of the renewables that we're building around the world are not supplementing, they're not offsetting fossil fuels, they're supplementing the energy infrastructure. So what we need to do is to have those renewables be replacing coal, and that is happening in the United States. This is the full data aren't out yet, but this year alone, coal consumption in the U.S. will be down another 10% or so, and we're about 50% from where we were at a peak only 15 years ago. So that's being replaced by natural gas, which is cleaner, and by renewables. Same thing's happening in Europe. You're seeing a country like England, where I was born, will maybe coal-free in its electricity sector by 2025 or so. So that's sort of the one segment of the economy that's truly decarbonizing, where a fossil fuel is being replaced by renewables. Right, so our energy appetite is growing, and you still have 300 million people in countries like India who don't have reliable electricity. So top priority for them isn't climate change, it's getting reliable electricity they can keep their food cool with and have lights on and things like that. So as much of that infrastructure that we can make be renewables, the better off we are. So India's building a lot of renewables, India's building a lot of coal, they have very little natural gas. So that's sort of the good and the bad news of the global picture. Here's a good news story, not a paper that I was involved with, but Corinne's work again. And these are templates, if you will. 18 countries where fossil fuel, in this case CO2 emissions, have declined over the last decade while their economies grew. Right, so there are countries where it's not a matter of reducing emissions by crippling our economies. There are good examples out there of countries that have been able to make this transition through renewables and other things and still have their economies grow. And they do that in two very large buckets through energy efficiency gains, so reducing the amount of energy that they need to generate to start with, and then of course by renewables replacing fossils. And the United States is one of those countries. Right, so these are just some examples. I think there are a lot of reasons for concern about climate, and there are some good signs that are happening too. All right, science-wise, what do we do in the Global Carbon Project when we look at a gas like CO2 or methane? We have to take into account the fossil fuel infrastructure, of course, but then we need to understand natural systems and the variation and uncertainties in those natural systems to be able to place the human emissions in its proper and full context. So in one of our, what I would call a budget, we have bottom-up estimates that would be, if you're an ecologist, you might study respiration in a field site and use chambers to measure the emissions of carbon dioxide from the soil into the atmosphere, or use towers, short towers like eddy flux and such. And then we would take all of these measurements and then sort of scale them up based on the area of a biome type, or the number of valves and flanges and things that you have on an oil and gas well, the number of tanks you have on an oil and gas well, and then estimate the number of oil and gas wells and their inventories for those things. So you can generate an estimate from the ground up, if you will, and then you want to have a totally independent estimate from the top down, because the atmosphere is the ultimate truth about at least what the net change is. And then we can use inversion models, satellites, latitudinal differences. So we don't, when something is emitted in a big source on the Earth, and the Earth is spinning this way, we can't really isolate where it's coming out this way, but we know information about this because it takes the time for the Earth to mix this way in its atmosphere. So we use latitudinal information to ask the question, is there runaway methane loss from permafrost systems? Because you'll see that in very far north systems, and we don't see evidence for that yet. But we are seeing evidence for increasing carbon dioxide losses from some of those systems. So we put all these things together, we ask, do they match? Sometimes they do, and sometimes they don't. Okay, so this is one just very overview article. This is the carbon dioxide cycle in a given year. This is an average for the past decade. So of the imbalance, if you will, in carbon dioxide emissions, almost 90% of them are coming from energy infrastructure. And a little over 10% are coming from deforestation and other land use changes. So traditionally, 100 years ago, this was the big term. And there are important changes now. There's a lot of focus on what's happening in Brazil with renewed deforestation there and the like. But most of the action is over here. Now, the interesting thing that some of you know, but perhaps not all, is that only less than half of the emissions in a given year stay in the atmosphere. So the concentration in the atmosphere should actually be going up twice as fast as it is if you were just looking at the source imbalance. But it doesn't, because about 30% of them are being absorbed by forests and other terrestrial systems and marine systems and aquatic systems. And I'll talk about that in a minute. So this is land-based here, and about another fifth is going into the oceans through increased productivity, but also just dissolving into the oceans and acidifying the oceans for our marine colleagues. So, one important science question for us going forward is, over this century, will these sinks continue to the same rate? Because, for instance, if forests stop growing as quickly here, then this term is going to go up, and the rate of increase will go up. So I want to explore this box for a few minutes and just give you an example of the kind of studies that we do. Right now, I mentioned Hal Mooney was my colleague at Stanford. I went to Stanford on a DOE fellowship as a postdoc, and it was one of the very earliest experiments that he and Chris Field and others led on an open-top chamber system. So imagine a grassland system with very small annual plants, and we increase the carbon dioxide concentration of the air in those chambers to simulate a future environment. So I went on to work on a couple of other systems. This was a project led by Wayne Pauley, USDA, in Texas. This was the first experiment in the world to provide a continuous gradient of CO2 from paleo concentrations, 200 all the way to current day, and then future, current day up to about 500 ppm. And this is a project that just closed a few years ago that I worked on with Wayne and others for many years. And then worked and helped lead the Duke FACE experiment. FACE is free air CO2 enrichment. This was the first forest experiment to provide a high CO2 world without using chambers or barriers that influence rainfall and temperature and things like that. So you have these PVC tubes here, there are holes in them, and then depending on the prevailing wind direction, a system that opens valves on those tubes so that the air is flushing over those trees in a high CO2 environment and adjusting the flow of CO2 and which valves are open to keep that air concentration in the sweet spot that you target. All right, so this paper I'll talk about, we just came out a month or two ago. We analyzed about 140 of these experiments around the world. And then we looked at different factors of climate, nutrient status, land and biome cover type, mycorrhizal interactions to ask the question, how much do we expect forest productivity to increase in the future? And then what are the constraints on that productivity? What are the things that limit it? And nutrient status would be an obvious one. If you don't have enough nitrogen or phosphorus, then you aren't really able to use that full amount of extra carbon dioxide as a food. All right, so why it keeps doing that? What do we find? This is work led by Cesar Torreira, a postdoc in our group, just came out. So this is a result stratified by mycorrhizal type. So arbuscular mycorrhiza and then ectomycorrhiza on the right. And then soil nutrient status. Now, if you're John Stark in the audience and others here, this is not a very sophisticated estimate of nitrogen availability, but a higher C to N ratio in the soils generally means less nitrogen availability for the plants and the microbes in that system. And it's a metric of nitrogen availability that we can actually get across all these sites instead of the more sophisticated ones. So, and then soil phosphorus availability on the bottom. And these kind of correlate with what these microbes are and are not good at these fungi are good or not good at collecting. So what you see here is the relative biomass response. So 0 would be no change in high CO2. Anything over this line is an increase. Anything under is a decrease. So first of all, you almost never see a decrease in productivity by increasing CO2, and that's not surprising as the substrate for photosynthesis. But as nitrogen availability decreases, at least through this estimate, the ability of the systems to respond, to use that extra CO2 goes down. So we can take a factor like this and then sort of make some estimate, if you will, of what might happen globally based on the soil status. So here for ectos, you've got a different relationship. As soil phosphorus availability goes down, then you see, again, a drop-off in the response of this system. So there's a core interaction, not a surprising interaction with nutrient availability, but it's modified also by mycorrhizal type and the microbial community in the soil. All right, so when you look at that, take those together, you get a result that looks like this. So we estimate that this CO2 response will continue a bit more modestly than it has in the past, so it'll slow down a bit. We project it'll store another couple hundred billion tons of carbon dioxide. So that's a lot. That's not nearly enough to compensate for all the fossil fuel emissions. But it's mostly, you can see the relative response here, and then the absolute response here. So most of the absolute response is down in tropical forests, the most biomass, and the highest productivity systems on land at least. So these are the kinds of ways that we hope to be able to say something about how these ecosystems might change. And of course, this does not take into account changes in disturbance. It doesn't take into account human management. Lots of other factors that will, if you remove a forest from the Amazon, then the CO2 response on Amazon rainforest is not going to matter, for example. So the many other factors that come in beyond just these sort of physiological responses. But these are key to projections of how much carbon dioxide will soak up. So let's go on. So how can we use systems in a more active way, perhaps, to keep carbon dioxide from going to the air? So one way I'll talk about briefly, we can restore historical losses of soil carbon from agricultural soils. Pretty much everybody knows this story. Through the process of regular plowing and such, we churn organic matter up. That makes it more easy for microbes to decompose. You're oxidizing that system. So there's been a lot of carbon lost from plowing around the world. Forest conservation and restoration is another real opportunity, and we're losing today about 5 billion tons of CO2 from a year from that. And then we have other effects from droughts and fire and things. So that's a big deal in California right now. California is trying to figure out, in what way should we be altering perhaps the forest that the state manages and such to reduce biomass in some cases for fire risk. So then of course, a lot of, maybe more importantly beyond climate, these other co-benefits that go along with this kind of management: biodiversity, conservation, fertility of our soils, fighting erosion and things like that. So here's a map. First of all, how much we have to know how much is there. This is an estimate that we've done, and we've done work on sort of global carbon pools for a long time. About 2,000 petagrams of carbon in soil. So there's way more carbon in soils than there are in the atmosphere. So although in a given spot there's not a lot, and you have to have a very extensive area to manage to make a difference, there's a lot of carbon down there. A lot more carbon in soils globally than in trees or plant biomass. So one of the things we're trying to understand is how other constraints might limit the amount of our estimates. So we're interested in new bedrock maps that have become available from the Department of Energy that constrain where the carbon is, groundwater depth, things like that I'm interested in, also from the standpoint of water uptake and plant functioning. But here's a work that Joe Sandeman and colleagues did, again, not one that I'm on, but they came out with a paper a couple years ago estimating that historical agricultural losses of soil carbon were about 200 billion tons CO2. So there's a big French-led effort called 4 per mil to try and increase the percentage of soil organic matter by a given amount every year. So we can try and put some of this carbon back into the system through less plowing, for instance. We can take some of that carbon out of the air, keep other carbon from going into the air. And relatively inexpensively is another key. There was a paper that came out just a few months ago. Bonnie and I were talking about this earlier today. This one got a huge amount of attention. Tom Crowther's group, led by Jean-Francois Bastin. So this paper basically said that we could plant trees almost to compensate emissions globally. And so this is a combination of restoration, but also imagine taking a climate map for the world and saying, well, what's the absolute limit where we could plant trees even where those trees aren't today? And how much carbon could we store on land by doing that? And their number is huge. A couple hundred gigatons of carbon. In this case, that'd be 600 plus billion tons of CO2. So this was a potential, not a potential. This was a Guardian story. Mind-blowing potential to tackle climate. It is kind of mind-blowing because there's a huge benefits to be had from restoration and conservation. But these kinds of estimates assume that we're going to take all of our land that's potentially available to do this. We're going to fill it with trees for 100 years, and then we're going to keep that carbon on the land. You can imagine like a box, and that's not how nature works. So, and on top of that, we have to ask, well, how would you get private landowners in the eastern half of the U.S. to do this? How would we have to change our land management on public lands in the western U.S. to maximize this kind of potential? So I think restoration and conservation are extremely valuable, but these kinds of estimates that say we can use land and basically get our way out of the problem of emissions, I think are to the extreme counterproductive. All right, well, last thing, I mentioned negative emissions. So what the heck is that? Well, here are just 3 cartoon scenarios of CO2 concentrations. This is Glenn Peters' work in Norway. So here's one way. So let's say you're worried about 1.5 stabilization, and you have this atmospheric bucket. We've got 500 billion tons left, 10, 15 years of emissions. We say, all right, we're going to run our energy system just as it is today, and then 15 years from now, we're going to turn everything off. Okay, that's one model. We can mitigate drastically starting today. So that would be whatever that is, 2, 3, 4% decline in CO2 emissions every year. Or more realistically, or less realistically, we can mitigate more gradually, and then we've got to take that carbon back out of the atmosphere. Right, and that's the negative emissions space, if you will. Badly named, but it is what it is. All right, so what is that? Well, first of all, what's a fossil fuel burning? Well, we take a pool, we burn it for energy, it puts CO2 into the atmosphere. There are 2 ways we can go carbon neutral. We can take a fossil fuel, burn it, capture the CO2, and put it back underground. So there are pilot projects underway to do that today. And it has worked already in places like Norway in the North Sea. The other way to go carbon neutral is to use plants to take the carbon out of the air, generate energy with those plants, then burn it without capture. Right? So your net is 0 in a very narrow sense. Negative emissions is combining those 2 things. So imagine in this case using plants or an industrial infrastructure to remove carbon from the atmosphere, burning it to make energy, and then sequestering CO2 underground. So the pathway is this to this. So the issue with it is that you have to have an energy source if you're using in industrial processes from direct air capture, or you have to have a lot of land to grow plants to capture billions of tons of biomass to do this with. Because if the coal emissions are 10 billion tons a year, which is about what they are, then we need to run that coal cycle in reverse. So here's just my last slide on this, and we'll go to methane. This is a little bit complicated, but let me just spend a few minutes on it. These are different approaches where we can use negative emissions. And I'm not advocating negative emissions to bet that that's the winning solution. But the farther we go down the emissions profile we're on now, the more it seems like it'll be needed. So there are different options that we can do. So there's something called enhanced weathering. You can imagine taking rocks, mining them, churning them up, and it's basically enhancing or speeding up chemical physical weathering. So you expose them to the air, they oxidize more quickly, they react with the carbon dioxide more quickly, and then you put them back underground. So it would be like expanding, quickening what would happen over thousands and thousands of years. All right, so that's one thing. Direct air capture would be to use an industrial array. Let's say you might take a solar panel, use the energy from that solar panel to take carbon dioxide out of the air through an amine process. These are technologies that exist today. And then capture that CO2 and put it underground. You could use trees, afforest, grow trees where they weren't before, reforest land, or you could use what's called BECCS, biomass energy with carbon capture and storage. That's the one on the right that I showed you before. All right, so the good news is these things are possible. The bad news is nothing's free, right? So first of all, some of these are more expensive than others. Direct air capture, the size of this pie, is a lot more expensive than using trees to capture your CO2. So here you're using trees and plants. Here you're using an industrial infrastructure. This is a lot more land intensive. This would take almost no land whatsoever. You would want to position these direct air capture systems over geologic reservoirs where you could put the CO2, for instance. Afforestation and reforestation is the cheapest here in the middle, but the most land intensive, and you're also not getting energy out of that system. So this really is the one way that you could couple negative emissions with actual energy generation. We could make electricity, run homes and cars and things with it. So this is kind of sort of somewhere between science and voodoo in a way. I mean, possible, but basically when you look at scenarios for temperature stabilizations that the assessment models use and such, they're all assuming, pretty much all assuming that something like this is going to be cost effective starting in 2050, 2075. So these models are already sort of betting that these kinds of things will happen, and it remains to be seen what we'll be willing to pay for at those kinds of scales. So let me finish with some information or some work on methane, something that we do a lot of work on in my group nowadays. And this is our sort of an infographic we produced for the global methane cycle a couple of years ago. And so what you have here, first of all, as general background, the methane cycle is far more influenced by human activity than the CO2 cycle is. So nowadays, more than half of all methane emissions to the atmosphere come from agricultural activities and fossil fuel mining, extraction, and use. All right, so about 60%. Natural sinks are here in green, so wetlands. Methane is generated naturally in anaerobic, low oxygen situations by microbes. So wetlands in the guts of cattle, that's why cattle emit methane. That's why diets matter for our climate solutions. So wetlands are the biggest natural source. We have some geologic seeps. Termites give off a surprising amount. Freshwater systems. It's taken up primarily by reaction with radicals like OH in the atmosphere, some destruction in soils, and then here are the ways that we're perturbing the system. So you see the fossil fuel production and use is about 100 million tons. These are teragrams now. Agriculture is our biggest source. Ruminants like cattle, goats and such, and rice farming, rice paddies. Same reason as a wetland, right? You have a waterlogged system, low oxygen environment, methane generating. And then biomass burning is both natural and anthropogenic because we set fires to clear land and such, and fires occur naturally as well. But really the actions are in these two places here, fossil fuel and ag, and then I want to explore the natural wetlands a bit too. So let's run through a couple of these. So where are methane emissions. The size of the pie tells you information about that. The color, green for wetlands, naturally, purple for other natural sources, ag in blue, fossil in gray, and then biomass burning in red. So you notice in the tropics that the sources are dominated by natural wetlands. You've got huge areas of the Amazon that flood, the Congo, Indonesia, and then also a lot of ag emissions of cattle and things like that. You get the temperate systems, big ag and fossil fuel components from oil and gas and coal extraction and use. And then in the far north, relatively smaller pie, so biggest in the tropics, intermediate, temperate, smallest of all up north, and it's fairly big oil and gas and also wetlands. You got a lot of flooded, waterlogged soil, cooler temperatures, so rates are lower up there. We don't see any evidence, as I mentioned, for runaway methane loss yet from permafrost, something you hear a lot about in the news. So we're not seeing that yet. That's good news. All right, from a bottom-up perspective, this would be an inventory approach. So this is sort of a pixel-based approach to where the best estimates are that methane is being emitted. So ag and waste here, biomass burning here, wetlands and fossil fuels. So I want to explore these two boxes and we'll finish. So wetlands, one of the grants that I lead is a grant from the Moore Foundation, and sort of the 5 biggest uncertainties that we identified in the global methane cycle are the rates of destruction by OH radicals. That's not something that I work on individually, but Philippe Bousquet in Paris leads that effort. We're looking at methane sources from freshwater systems, wetlands in particular. I'll talk about a new tower synthesis that we're leading, high permafrost releases, and then thermogenic methane that's mixed from natural and oil and gas and coal-based sources. So one of the things that we're doing through this grant is setting up a new tower network around the world. We have, through a collaboration with many, many scientists, there are already about 200 tower sites at the eddy flux scale, sort of the landscape scale, measuring fluxes on a gross and a net basis, mostly on a net, and the gross fluxes are estimated. Right, so you can see the distribution of these sites are primarily temperate, not surprising. Some in high latitudes, very few in the tropics, but that number is increasing rapidly. So of these 200 tower sites, and let me be clear, we didn't go out and establish these 200 tower sites. We have some, but this is a matter of sort of assembling the community. We have now data for 80 tower sites that we're making publicly available, that we're analyzing. I'll talk about for a few minutes. And again, all of these data will be released. In climate space, this new network covers this kind of distribution. This is rainfall or precip on the y-axis, so dry to wet. Air temperature cold to hot. And you can see the distribution of space across there. So not everywhere, but not bad, really. So these are the kinds of data, and we're just beginning this analysis, but these are the kinds of data that we can get. We can make an estimate of emissions associated with a particular habitat type. So in a very, very coarse way, you can imagine with these kinds of estimates, and the acreage of these globally, you can make some estimate about the emissions from different habitat types. So you see that swamps and marshes are higher than the wet tundra, salt marshes, coastal systems, and such. And then we can look at temperature responses. Now, these are temperature responses obtained across sites, not temperature responses by looking at variations in years within sites, and that's very, very different. So these relationships are quite steep. This is a Q10 of about 3.4, but this is not a physiological reaction, and I should also point out that this is a log-log plot. But you can see, the direct effect of air temperature in this case, and then mean soil temperature turns out to be an even better predictor. So the two things that we really need globally to estimate methane emissions well, 3 things, shall we say. We need the productivity, how much carbon is going into the system from plants. We need the temperature profile on a real-time basis, and we need to know some status of the redox in soil. So if it's flooded, how low oxygen is it? Is it a waterlogged system? And one of the biggest uncertainties we have in this, and one thing we're working on, is that it's hard to see inundation from satellites in space. It's easy to see open water, but it's difficult to see through a high leaf area wetlands canopy, for example. So one of the things that a couple folks in my group work on is using remote sensing to estimate inundation better, so we can make a real-time sort of satellite-based estimate of inundation rather than working with static maps. So that's an example of some of what we're doing. And let me finish just with a few examples from, so now we're in the sort of the non-natural solutions, if we will. So about 10 years ago, after giving many, many climate change talks and discussing the CO2 results and these experiments, I got tired of not working on energy infrastructure because most of the box is coming from fossil fuel activity. So, and I guess it harkens back a little bit to my earlier job with Dow Chemical, my first degree as a chemical engineer and such. So some of this work kind of fuses an ecosystem balance approach, if you will, with human systems now instead of forests and grasslands. So these are the kinds of things we do. I'll talk about just briefly: fly helicopters and film oil and gas wells, map leaks across city infrastructure, things like that, and try and use that information to reduce emissions to the atmosphere. So I'll just go through a couple of things. Now, first of all, methane, the dominant component of natural gas, leaks out all along the supply chain, from extraction all the way to use. So we need improvements along that chain entirely. This is the EPA's estimate. So let me just give you a couple of examples. Here's one we did. This is led by David Lyon, actually, with the Environmental Defense Fund. So this is we flew 8,000 well pads across the United States randomly. So this is like a restaurant inspection, right? You show up in a helicopter. You have a particular infrared camera, so these emissions are not visible with the naked eye. You film a particular well pad, and you can tell whether it's leaking or not. And we can't get a kilograms per hour with that kind of camera, but we can get a qualitative small, medium, and large kind of thing. So this is in the Bakken in North Dakota as one of the places. So let me just give you an example of what you might see. This is not normal, but it's not unnormal enough. So you're, let's see if this is going to start. Can't tell if this is going to go or not. I might have to skip it. It's not going to work. That's never happened to me before. So this is basically a pan. Here's a couple of tanks you see. So this is a pan in a helicopter, black and white image. You fly. Oh, so it's just taking a long time to project. Well, without seeing the video, as you fly over, this is what you see. So this is a black cloud coming out of the top of that tank. Right, and that's invisible to the naked eye. That, in this particular case, that's a hat. That's human error. So someone has taken product out of that tank and forgot to flip the hatch closed. So there's nothing like that in the inventories that we have for counting valves and flanges and things like that. All right, so these kinds of results. So what do we find? Well, where you are matters. The percentage of sites with large emissions was about 1 in 25 nationally. That would be a large one, the photograph I just showed you. But there was a huge difference, 1% in the Powder River Basin of Wyoming to 14, 1 in 7 in the Bakken. And the highest emitters are the oil and gas, particularly the oil plays, right? So the Permian in West Texas, the Bakken in North Dakota, because they're making all their money on oil. In the Bakken, they're flaring 25 to 30% of the natural gas because they can't get it to market in a pipeline. So they're just burning it. So how much incentive do they have to dial down every leak in the system for a product that you're not even using and getting paid for? And also in these oil-producing plays, this is a tank battery in the Bakken. You've got more valves, more tanks, more infrastructure, and every one of those pieces has a small but positive probability of emitting or leaking or failing. So anyway, tanks and hatches were the biggest source that we saw. So we feed this information back to the companies, but we also anonymize it and make it public so that you can look at different parts of the U.S. Why are some regulatory frameworks more successful than others? Are operators more successful than others? And why? Okay, last example, do some older work to newer, but we did the first maps, publicly available maps of natural gas leaks. So here, imagine taking, say, a new laser-based instrument where you can measure a methane concentration and nowadays an ethane concentration in real time, and you put that in the back of a car and you start driving. And I probably am safe to say that I'm the only person in this room who's driven every block of the city of Boston, trolling like fish. So you drive around, nothing happens, and then your instrument pings. And in Boston, your instrument pings about once every quarter mile. So Boston has a natural gas leak detectable from these instruments every quarter mile, 4 per mile or so. So this is Washington, D.C. A map of D.C. The Washington Post did an app on based on our data that we produced for the city. We mapped 6,000 leaks across D.C. There's the car, anemometer on top, so you know the wind direction. And if you get a ping, you know which side of the road the leak's coming from. And then you can hop out of the car for a particularly big one and sample the gas and make sure it's not microbes in a sewer and it's actually natural gas in the city. So here's Boston, about 3,300 leaks. Red is road miles driven. Yellow are the spikes. These are concentrations, not flux estimates, which I'll come to. But number one predictor in Boston of a leak, old cast iron piping. Some of this pipe is 100 years old. It was laid not that long after the Civil War, still in use today because it's expensive to dig up our streets. This is like old water mains too. They leak like sieves. So the day after that paper came out, that was led by Nathan Phillips, I should say, my colleague in Boston. The mayor of Boston commented on it. Markey was a congressman at that time instead of a senator. He released a letter and report about it. The next year, Massachusetts passed a pipeline replacement bill, a safety bill, to repair and replace old cast iron pipes. So it gave the companies more money to repair those pipelines. So the companies wanted to be able to repair them, but the utility commissions cap how much money they can recover from consumers, because what we care about as consumers is keeping our rates down. So this kind of approach allows them to front load the repairs. But the interesting thing is that consumers, we pay for gas that leaks out of every one of those bars that you see, right? The companies are paid for that gas. So again, what's their incentive for really dialing down every leak as much as possible when they're paid for a product anyway? Right, so for me, this is a win-win outcome because the companies extract some benefit, and it wasn't driven by climate. It was driven by concerns about explosions and safety. And I think for me, that's become an increasingly important message for a society where we're split over climate emergencies and that. But if the same things that lead to climate solutions also make explosions less likely, the two biggest sources of pollution in the United States are car emissions and coal-fired power plants. So green economies help us reduce those emissions. They'll save tens and tens of thousands of lives by making a switch to electric cars or to natural gas and renewables. Right, we're still importing 3 million barrels of oil a day from OPEC countries. So why would we want to reduce our vehicle fuel efficiency standards at a time when we're still at war in the Middle East and still importing oil from countries whose regimes we don't support? So regardless of somebody's political views, there are benefits to these kinds of changes that really you don't even need climate to support them, and economic reasons too. Just to attribute cause, and I'll finish, this was a study led by Steve Wofsy's group in Boston, but here we wanted to get the amount that's coming out in Boston, and it's hard to scale up from 3,300 leaks to what the total amount is. So we tried to go from the top down in this case. We put sensors on top of the skyscrapers in the city, sensors outside the city, so you had quality and concentrations of the gases in the air as it moved in, became dirtier in Boston. And then we looked at two things. We looked at isotopes, but we also looked at the concentrations of methane and ethane. So ethane is 2 carbon molecules, methane 1. Ethane isn't produced by microbes. So you can sort of root out the biological side of the equation by using the ratio. Our hypothesis was if most of the gas over Boston was coming from natural gas, it ought to look like the same ratio of methane to ethane that's flowing through the pipelines that feed the houses in Boston. So that's what we did. And we had that data information publicly available. That's the blue line. The red line and the black is what we observed. So in this case, in winter, 90% of the methane building up over the air in Boston was coming from natural gas use. We didn't know where it was coming from, homes, leaky pipelines, industry. In summer, the amount was the same, but the percentage was lower because there's a lot higher biological activity in the warmer summer conditions. So really pretty airtight data. And finally, this was 2.5 times higher than the state said it was based on their inventory. So these are the kinds of approaches where we can use top-down estimates to figure out the quantity and really constrain that pretty tightly. Finishing up, here's a picture of Times Square that I took for the car. So we wanted to look at cities that had and had not repaired their pipelines. So in addition to DC and Boston, we added Manhattan. We added Cincinnati and Durham, North Carolina as 2 cities that had already completed old cast iron pipeline replacement programs and to ask how much better do they make it? And maybe not surprisingly, a lot. We had 1/10, 1/20th the number of leaks in those cities than in the cities that hadn't implemented such programs. So these things make a huge difference, and they're making our systems not just cleaner environmentally, but a lot safer as well. A few reasons for fixing street leaks, a couple $2 billion a year that we pay for. Jobs, the unions are all behind repairs. Accidents are extremely rare, but they happen. There's still a dozen or so people killed a year on average in natural gas explosions, sometimes human error, sometimes old infrastructure. $100 million or more in property damage. Hydrocarbons catalyze ozone formation, and yes, climate, if you want to use that as a justification. I'll finish here. The place in the natural gas supply chain that has had almost no attention is homes. So post-meter analyses, the company's responsibility stops when the gas goes through your meter if you have gas to your house. So we're looking at stoves, water heaters, furnaces, and things like that, because we're trying to figure out where's all that extra gas coming from in cities like Boston. We don't find it just from the distribution systems alone. So these are a couple students, Eric LaBelle, Simone Spicer, and our group that are doing that work. And then we also look at old oil and gas wells. These are legacy issues of what happens to wells that were abandoned 50, 75, 100 years ago, and how leaky are they, and where are they? So I will stop there. As I said, I tried to provide an overview of sort of the philosophy of our work in the Global Carbon Project. I've given you a few hints of some of our work related to greenhouse gas emissions. Tomorrow I'll focus more on plants, soils, and traditional ecology, but thank you for your attention.
We certainly have time for questions.
Do you want a mic, or I can repeat the questions?
Okay, so given the more potent effect of methane than CO2, I've heard the figure that if we had 3% leakage of methane from the source to the final usage, that it would be on par with coal in terms of the dirtiness of it. Do you think that 3% is accurate, or is it higher or lower? And how close do you think our leakage rates are to that?
Yeah, so the question in back, for those of you who can't hear, is how much methane, sorry, let me back up. For electricity, natural gas emits about 1/2 the carbon dioxide that coal does. So natural gas is better than coal independent of CO2 because it has no particulates, no mercury, lots of other things. But CO2 alone, we count on a 50% reduction every time we swap a coal plant for a natural gas plant. What John's asking about is, well, how much extra methane leakage is there? Methane's far more potent than CO2, and if the methane leakage from natural gas infrastructure is a lot higher than what's coming out of coal mining, and it is, then we lose some of that CO2 benefit. And so there is this number, we don't know exactly what it is, and it depends on the time frame. Methane doesn't last as long as the atmosphere, so when you look at a 20-year time frame, methane's extremely potent, like 80, 90, 100 times more potent than CO2 on a mass basis. 100 years out, it's more like 30 times more potent. So when you get to this number like 2.5 or 3%, the greenhouse gas cost of that methane leakage offsets any CO2 gain in the air. And so we are probably not at 3% in this country, but we're not far away. My estimate would be, based on many people's work, that we're much higher than EPA's suggestion and industry suggestion, and probably at least 2% on average. So we're not getting the climate benefit we think we're getting from the switch from coal to methane and natural gas. There are other reasons to make that switch, and using satellites and other new technologies, I believe we are in a position to be able to find large leaks much more quickly now, say in the next 5 years, than we have in the past. US and anywhere in the world, Russia, Nigeria, wherever you're working. But right now, we're not realizing the full benefit, and the number's higher than our government says it is. Other questions? In back?
You talked about trees helping mitigate the greenhouse gases, but you didn't specify kind of trees. What I'm thinking is, instead of it being a cost, it could be a profit. You only plant fruit-bearing trees, like fruit and nut trees, and you actually plan to harvest them at all. Within a year or two of harvesting, you're actually making money off the trees, you're solving a food problem, and you're taking care of this greenhouse gas thing. Did your analysis analysis look at food-bearing trees and the cost of how that would?
Yeah, no, it's a great question. I mean, the notion of, what, I didn't specify trees. I mean, most of the biomass, as I showed in that graph, is locked up in tropical forests and such. But anything we can do to increase carbon storage, and fruit trees can certainly be part of that solution. There aren't, currently anywhere near enough orchards and such to make a really huge dent in the billion ton scale. But it's an important component. It's just like plowing and other things associated with ag. Anything we can do to reduce emissions in the ag sector is as important as it is in the industrial sector. So yeah, I agree with you. It's a good point. Other questions? Quiet group. Mm-hmm.
This was a detail in the setup for your talk, so it's not your research, but I was curious about is it
Le Carré, Corinne. Mm-hmm.
2019, where there's countries that have decoupled economic growth from greenhouse gas emissions. Does that account for only the production within the country or also the consumption? Because you can have, say, Switzerland, the US, and we are totally dependent on China emitting lots of greenhouse gases in order to have the material well-being that we have in our country.
Yeah, so that's a great question. So that's a difference between what we would call territorial emissions and consumption-based emissions. And the territorial emissions are what we see, right? So we can see a smokestack in China or in the United States and measure the emissions. But the spirit of the question is, well, what about that computer that I own over there on that table? That computer was produced in China, so my emissions associated with that computer are attributed to China's pollution and to people in China. And so we do take that into account, and Corinne's analysis does take that into account, and we produce estimates both of territorial emissions and consumption emissions. So in the US, our emissions would be about 10 to 12% higher than they are if you just measure the CO2 that's given off by our energy infrastructure. China's would be less. But yes, that includes those 18 to now 20-ish countries, and that includes consumptive-based emissions as well. Mm-hmm.
So what percent of, maybe you stated that number and I missed it, of methane emissions could be attributed to these leaks, mainly around kind of domestic operations? Because that's one of the things that people are missing are actions that they can take in their day-to-day life. I cannot now shift my local power, production from coal to solar, but I can maybe test for leakage in my gas system.
Okay, so the question is about leakage and what we can control individually. Well, we can't. There's not much we can do individually about a particular leak on a street. We call the natural gas company. We can make decisions about the appliances that we buy. When we heat our homes, is the next appliance that you buy going to be an electric heat pump or a natural gas furnace? There are new induction-based stoves that are essentially instantaneous that could replace the natural gas stove that we have. So I would say the consumer choice in appliances is one way. We do, depending on where you live, we do have some control over the electricity, the source of electricity, or we can, some places you can pay extra to request renewables, which is really an outdated view. We were talking about this at lunch. I mean, so at Stanford, we just signed a contract for 50 megawatts of electricity at just over 2 cents a kilowatt hour. I mean, that's cheaper than, even if you include subsidies, that's cheaper than coal. I mean, this transition is happening now based on price, not just on climate concerns. And yes, there are issues that we need to take into account for intermittency and storage and things like that. But it's really economics as much as anything else. So where you have the option to buy an electric car and you have a mostly renewable system, buy an electric car when your electricity is coming from coal is not a climate win. But if you can live in a system or have renewable power, have solar panels on your house and power an electric car, that's a win. So we do have some control over.
But if you would stop natural gas use in the private sector, would that make a dent in methane emissions?
Heck yeah. I mean, that's 100 teragrams of methane going to the atmosphere associated with our energy use. In the back first, you were first, and then here.
States like Utah really love to include methane as part of a renewables sort of portfolio. And given the research that you've done, what's your assessment of methane and natural gas as a bridge fuel and some of the economic dynamics involved in that?
Yeah, so the question's about natural gas as a bridge fuel. First of all, as an environmental scientist, the transition from coal to natural gas is a positive transition. Right? I mean, natural gas pollution doesn't kill tens of thousands of people a year. It doesn't cause 100,000 cases of childhood asthma in the United States. And these are low estimates for those kinds of numbers. The problem is we build a new natural gas plant and it's still emitting 50% of the carbon dioxide in 40 years. So maybe if we can, the coal is being phased out in this country. If the natural gas plants that we build now can be made so that they can be retrofitted with carbon capture and storage technologies, that's one thing that could help. But anything we can do to push renewables as quickly, and low carbon, it's not just wind and solar, anything we can do to push those as quickly as possible keeps that 40, 50-year infrastructure from being built in the first place. So I do think there's a place for natural gas as a bridge fuel. But my view of what a bridge fuel is and the president of Exxon's view of what a bridge fuel is would probably be pretty different. And I work with oil and gas companies. I don't say that lightly. But how long is that bridge? And how explicit are we about that bridge? And what's the total amount of extra emissions we're likely or willing to support to get there? I'll let you answer the question too, maybe. But you want to answer it?
Well, I mean, I think in a place like Utah, you have to also take into account something like public subsidies for that. Where we're using things like the consumer impact bond, for example, that should be used to mitigate the impact on rural communities based on extraction and used to subsidize fossil fuel infrastructure. So there's both kind of a scientific question, a policy question, and a values question kind of built into that. And I think that it really involves some of the sort of communication work that you're talking about in terms of needing to communicate these scientific findings to audiences, but even more so, making a more informed debate about what these options are.
Yeah, I really like that response. And another part of it is, to what extent can we get that leakage that John asked about down closer to zero instead of 1.5 to 2.5% of all the gas that's produced. That makes a big difference in that calculation of a bridge fuel. Maybe one more here. It's almost 5 after.
So it seems like we're going to fly right by the 1.5 degree warming scenario. Very likely we'll fly right by the 2 degree. And academia has done an incredible job laying out that problem, helping us understand where all the sources are, and all of the many, many implications of it, and how it touches every part of our economy, our society, and everything. Academia has done great at talking the talk. What do you think academic institutions should be doing to walk the walk and actually get our own emissions down and demonstrate just how important it is and how you can change business?
Yeah, great. So the question is, what should we be doing locally? And by locally, in this case, we mean the institutions that we're a part of. What is USU doing? What is Stanford doing? What are other universities around the world doing? Institutions of learning. I know a little bit about what USU is doing, partly from what I've read, and then partly from asking people and hearing from people today. At Stanford, Stanford has financially some advantages that not all schools have, but there are a lot of schools making very aggressive pledges and putting some of these pledges into action. So we're pretty close to being carbon neutral electricity-wise at Stanford. So we've signed two large solar contracts in the past 5 years, and then done a huge retrofit of the heating and cooling system on campus to recapture energy from that system. We still have some natural gas that goes into our system, but we're pretty good on that front. And again, it turned out it didn't have to be for climate. I mean, the prices for industrial solar in the southwestern U.S. are incredibly low right now. Other kinds of emissions are more difficult, right? Stanford's made a pledge to be waste neutral by 2030. I have no idea what that means, right? I don't know if that means nothing goes to the landfill. If we crush up glass but recycle it, is that really being zero emissions? No, it's not. So, but these kinds of pledges matter too. Commuting, there's nothing I do in my life that has more emissions than than traveling, right? I just got on a plane and flew to Logan, Utah, and that source swamps anything else I do individually. So we need to think about commuting, and we're getting there with electric cars slowly but surely, but there isn't any obvious electric plane beyond small planes that can now go about 500 miles, with batteries and such. So the transportation sector is the hardest to decarbonize, and the air sector is the hardest of the hard to decarbonize. So I think we need to take into account, first and foremost, the electricity we generate on campus and pushing the university to make that renewable. And after that, we need to cover Scope 2, Scope 3 emissions around consumption, waste, commuting, things like that. So my answer to you to the students would be push the university and push them hard to be more aggressive. So thanks for your time.